Hi everyone. Today we are going to be going through the Simplex algorithm, and thereafter we are going to go through some calculations practically. So the objectives of this topic, one is expected to understand the following at the end of this topic. Number one, the basic rules for implementing the Simplex algorithm. Number two, how to find an initial basic feasible solution for a linear program. Number three, differentiate between feasible and non-feasible solution, optimal and non-optimal solution. So we have the simplex method, non-graphical solution procedure. Graphical solutions are only applicable for LPPs involving two variables. The most realistic applications of a linear program involves more than two variables. Simplex method is an algebraic procedure for solving systems of equations where an objective function is to be optimized. It is an iterative process which identifies a feasible starting solution. Iterative processes because a specified set of solution steps are repeated until a conclusion is reached regarding the solution of the problem. The procedure then searches to see whether there exists a better solution. Beta is measured by whether the value of the objective function can be improved. If a better solution is signaled, the search resumes. The generation of each successive solution requires solving a system of linear equations. The search continues until no further improvement is possible in the objective function. In all graphical solutions, it was observed that the optimal solution to an LP is located at an extreme or corner point of the solution space. This observation is the foundation of the general algebraic solution algorithm for LPs. The algorithm is called the simplex method. To facilitate the algebraic identification of the extreme points in a solution space, LP models have to be written in standard form. In standard form, constraints are stated as equations. In standard form, the objective function is of the maximization or minimization type. Minimization of a function is equivalent to the maximization of the negative expression of this function. All constraints must be stated, expressed as equations, except the non-negativity constraints. The right-hand side of the constraints are non-negative. All the decision variables are restricted to non-negative values. Notes: to convert a minimization problem to maximization problem, simplify, multiply the function to be minimized by -1 and maximize this function. Convert inequality constraints of both types to equalities. The inequality constraints are changed to equality constraints by adding or subtracting a non-negative variable on the left-hand side of such constraints. In such constraints, the right-hand side represents the limit on the availability of a resource, in which case the left-hand side will represent the usage of this limited resource by the activity variables of the model. For each such constraint, a non-negative variable called a slack variable is added to the left-hand side of the constraint. Slack variables serve the function by balancing the two sides of the equation. It represents unused amount of the resource. Let's take an example. A manufacturing firm produces two products, A and B. Each of these products must be processed through two different machines. One machine has 24 hours of available capacity, and the second machine has 16 hours of available capacity. Each unit of product A requires 2 hours of time on both machines. Each unit of product B requires 3 hours on the first machine and 1 hour on the second machine. The incremental profit is $6 per unit of product A and $7 per unit of product B, and the firm can sell as many units of each product as it can manufacture. Determine how many units of product A and B should be produced within the limits of available machine capacities. Let's look at the solution. The final formulation of the model, we have maximize z is equals to 6x1 plus 7x2, subject to 2x1 plus 3x2 is less than or equal to 24. This is the available hour capacity for machine 1. 2x1 plus x2 is less than or equal to 16, available hour capacity for machine 2. Then we have x1, x2 is greater than or equal to 0. So consider the two constraints for product mix model. So we have the first equation, 2x1 plus 3x2 is less than or equal to 24, available hour capacity for machine 1, and 2x1 plus x2 is less than or equal to 16, available hour capacity for machine 2, where x1 and x2 represent the number of units produced and sold for product A and B respectively. The two constraints represent limited hour availability for the two machines. The right-hand side of the constraint represents the number of hours available for each machine per day. The treatment of these constraints is to add a slack variable to the left-hand side of each, i.e. 2x1 plus 3x2 plus s1 is equals to 24, 2x1 plus x2 plus s2 is equals to 16. The slack variable s1 and s2 represent the number of unused hours for each machine. For example, if x1 is equals to 6 and x2 is equals to 2, this suggests that we produce 6 units of product A and 2 units of product B. If we substitute these values in the constraints, we have 2x1 plus 3x2 plus s1 is equals to 24. Substituted the values, we get that s1 is equals to 6. 2x1 plus x2 plus s2 is equals to 16. We substitute the values and get that s2 is equals to 2. 18 hours will be used for production in machine 1 and 14 hours in machine 2. The slack variables would assume the values of S1 is equals to 6 hours, S2 is equals to 2 hours to balance the equation. The interpretation of these values in that producing 6 units of product A and 2 units of product B would result in 6 hours being left over in machine 1 and 2 hours in machine 2 unutilized. Let's take another example. A firm manufactures 2 products, each of which must be processed to department X and Y. The table below summarizes labor hours, requirements per unit for each product in each department. Also presented are weekly labor hour capacities in each department and respective profit margins for the 2 products. The problem is to determine the number of units to produce of each product so as to maximize total contribution to fixed cost and profits. So the final formulation is maximize z is equals to fx1 plus 6x2 subject to 3x1 plus 2x2 is less than or equal to 120, 4x1 plus 6x2 is less than or equal to 260, x1, x2 greater than or equal to 0. So consider the 2 constraints for product mix model, where x1 and x2 represent the number of units produced and sold of product A and B respectively. The 2 constraints represent limited labor availability in the 2 departments. The right-hand side of the constraints represent the number of hours available in each department per week. For example, if x1 is equals to 10 and x2 is equals to 30, suggest producing 10 units of product 1 and 30 units of product 2. If we substitute these values in the constraints, we get that S1 is equals to 30, S2 is equals to 40. 90 hours will be used for production in department X and 220 hours in department Y. The slack variables will assume the values of S1 being 30 and S2 being 40 to balance the equation. The interpretation of these values is that producing 10 units of product A and 30 units of product B will result in 30 hours being left over in department X and 40 hours being left over in department Y. So for each such constraint, a non-negative variable E, called a surplus variable, is subtracted from the left-hand side of the constraint. This variable serves the function by balancing the 2 sides of the equation. It represents the values that exceed the minimum requirements. In addition to subtracting a surplus variable, and a negative variable A, called an artificial variable, is added to the left-hand side of the constraint. The artificial variable has no real meaning in the problem. Its only function is to provide a convenient starting point for the simplex. Assume in example 1 that combined production of the 2 products must be at least 6 units. This gives 6x1 plus 7x2, 2x1 plus 3x2 is less than or equal to 24, 2x1 plus x2 is less than or equal to 16, then x1 plus x2 is greater than or equal to 6. This is the combined production. In standard form, subtracting a surplus variable and adding an artificial variable, we get 2x1 plus 3x2 plus s1 is equals to 24, 2x1 plus x2 plus s2 is equals to 16. Then we have x1 plus x2 minus e3 plus a3, which is equal to 6. The subscript e3 indicates the constraint number. That is, Each of the variable is assigned a subscript that corresponds to the constraint number. If x1 is equals to 6 and x2 is equals to 2, suggests we produce 6 units of product A and 2 units of product B. If we substitute these values in the constraint, we have x1 plus x2 minus e3 plus a3 is equals to 6. So that will be 6(1) plus 2 minus e3 is equals to 6 and e3 is equals to 2. The interpretation of the surplus variable E3 is that combined production of 6 units of product A and 2 units of product B exceeds the minimum requirements by 2 units. Let's take another example. Assuming example 2 that combined production of the two products must be at least 25 units, i.e. x1 plus x2 is greater than or equal to 25. Write down the new LP model in standard form. Interpret the value of the surplus variable E3. We see that 3x1 plus 2x2 plus s1 is equals to 120, 4x1 plus 6x2 plus s2 is equals to 260, and we get x1 plus x2 minus e3 plus a3 is equal to 25. The subscript e3 indicates the constraint number. Each of the variable is assigned a subscript that corresponds to the constraint number. So if x1 is equals to 10 and x2 is equals to 30, suggests we produce 10 units of product A and 30 units of product B. If we substitute, we get that A3 is equals to 15. The interpretation of the surplus variable E3 is that combined production of 10 units of product A and 30 units of product B exceeds the minimum requirements by 15 units. For each equal constraint, an artificial variable is added to the left-hand side of the constraint. If a constraint has a negative right side value, the constraint can be multiplied by -1 to make the right side positive. Notice, for inequality constraints, the sense of the inequality reverses when multiplied by a negative number. So let's take an example. Transform the following constraint set into standard form. x1 plus x2 is less than or equal to 100, 2x1 plus 3x2 is greater than or equal to 40, x1 minus 2x2 is equal to 25, x1, x2 is greater than or equal to 0. We get the solution being x1 plus x2 plus s1 is equals to 100, 2x1 plus 3x2 minus a2 plus a2 is equals to 40, x1 minus 2x2 plus a3, x1, x2, s1, e2, a2, a3. Let's take another example. Maximize z is equals to 3x1 plus 2x2 plus 5x3 subject to 2x1 minus 3x2 less than or equal to 3, x1 plus 2x2 plus 3x3 greater than or equal to 5, 3x1 plus 2x3 less than or equal to 2, x1, x2, x3 greater than or equal to 0. So the slack variable and surplus variables introduce no profit. So their coefficients in the profit equation are 0. Z is equals to 3x1 plus 2x2 plus 5x3 plus 0s1 plus 0e2 plus 0a2 plus 0s3 subject to 2x1 minus 3x2 plus s1 is equals to 3, x1 plus 2x2 plus 3x3 minus e2 plus a2 is equals to 5, 3x1 plus 2x3 plus s3, x1, x2, x3, s1, e2, a2, s3 is greater than or equal to 0. So some points to note: when LP problems, where all constraints are restated as equalities and supplemental variables have been added, the resulting system of constraint equation has more variables than equations. A LP in standard form includes m simultaneous linear equations in terms of n unknown variables, where m is less than n. The variables can be considered in two sets: n minus m variables, which are assigned a value of 0, the remaining m variables, whose values can be determined by solving m equations simultaneously. If the m equations yield a unique solution, then the associated m variables are referred to as basic variables, and the remaining n minus m0 variables are referred to as non-basic variables. The unique solution from the m equations is called a basic solution. If all the variables have non-negative values in the basic solution, then basic solution is feasible. Otherwise, it's an infeasible solution. So we have number 1, feasible solutions. Feasible solution is any set of values for the n variables which satisfies the standard equation in a non-negative constraint. For the standard equations, 2x1 plus 3x2 plus s1 is equals to 24. 2x1 plus x2 plus s2 is equals to 16. Suppose x1 is equals to 5 and x2 is equals to 2, then s1 is equals to 8 and s2 is equals to 4. Basic solution is any solution obtained by setting n minus m variables equal to 0 and solving the system of equations for the values of the remaining m variables. The m variables solved for all are called basic variables. The remaining n minus m variables, or those which have assigned a value of 0, are called non-basic variables. Example, 2x1 plus 3x2 plus s1 is equals to 24. 2x1 plus x2 plus s2 is equals to 16. The number of equations is equals to 2, that is m. The number of variables is 4, which is n. So the 2 times 4 system, number of variables to be assigned is 4 minus 2, which is 2. Suppose x1 and s1 are set equal to 0. Then 2 into 0 plus 3x2 plus 0 is equals to 24 for machine 1. Then 3x2 is equals to 24, leaving that x2 is equals to 8. 2 into 0 plus x2 plus s2 is equals to 16 for machine 2. 8 plus s2 is equals to 16, leaving s2 be equal to 8. The basic solution for the system is x1 is equals to 0, s1 is equals to 0, x2 is equals to 8, s2 is equals to 8. x1 and s1 are non-basic variables, while x2 and s2 are basic variables. Suppose that x1 and s2 are set equal to 0, then 2 into 0 plus 3x2 plus s1 is equals to 24. So we have 3x2 plus s1 is equals to 24. 2 into 0 plus x2 plus 0 is equals to 16. Using equation 2 in 1, we get s1 is equals to negative 24. The basic solution for the system, x1 is equals to 0, s1 is equals to negative 24, x2 is equals to 16, s2 is equals to 0, with x1, s2 as non-basic variables and x2, s1 as basic variables. Basic feasible solutions are unique solutions which satisfy the non-negativity constraint. Using the same example, 2x1 plus 3x2 plus s1 is equals to 24 for machine 1. 2x1 plus x2 plus s2 is equals to 16 for machine 2. Setting x1, x2 equal to 0 gives s1 equal to 24, s2 equal to 16. Therefore, x1 is equals to 0, x2 is equals to 0, s1 is equals to 24, s2 is equals to 16 is a basic solution. Since all 4 variables satisfy the non-negativity restrictions, this is a basic feasible solution. Suppose x1 and s1 are set equal to 0, then 2 into 0 plus 3x2 plus 0 is equals to 24, 3x2 is equals to 24, x2 is equals to 8, then 2 into 0 plus x2 plus s2 is equals to 16 for machine 2, 8 plus s2 is equals to 16, so s2 is equals to 8, so x1 is 0, s1 is 0, x2 is 8, and s2 is 8 is a basic solution. Since all 4 variables satisfy the non-negativity restriction, this is a basic feasible solution. Suppose x1 and s2 are set equal to 0, then 2 into 0 plus 3x2 plus s1 is equals to 24 for machine 1, 3x2 plus s1 is equals to 24. 2 into 0 plus x2 plus 0 is equals to 16, then x2 is equals to 16. So x1 is equals to 0, s1 negative 24, x2 16, s2 0 is a basic solution. Since s1 does not satisfy the non-negativity restriction, solution is a basic but not feasible solution. The optimal solution can be found by performing a search of the set of basic feasible solutions. This is what the simplex method accomplishes. It begins with a basic feasible solution consisting of 2 pools of variables, i.e., m basic variables and n minus n non-basic variables. The simplex method determines whether the objective function can be improved by exchanging a basic variable and a non-basic variable. If an exchange will result in an improvement, an existing basic variable is set equal to 0. An existing non-basic variable is included in the pool of basic variables, and the system of equation is resolved with a new set of basic variables to form a new basic solution. A determination is made again as to whether a better solution exists. If so, another exchange takes place and the process repeats itself. The entering variable is a current non-basic variable that will enter the set of basic variables as the next iteration. Leaving variable is a current basic variable that will leave the basic solution in the next iteration. So we have the steps of simplex algorithm. Number 1, using the standard form, determine the starting basic feasible solution. Number 2, select an entering variable from among the current 0 non-basic variables, which when increased above 0 can improve the value of the objective function. If none exist, stop. If there are several possible entering variables, choose the one with the most negative coefficient. In case of a tie, for the most negative coefficient, choose arbitrarily. We'll choose the one in the farthest left. Select a leaving variable from among the current basic variables that must be set to 0 when the entering variable becomes basic. For each positive entry in the entering variable column, calculate the ratio. Choose the smallest ratio, the basic variable for the row where if there exists no ratios to calculate because all entries in the entering variable column are negative or 0, stop. The problem is unbounded. In case of a tie, for the smallest ratio, choose arbitrary. We'll choose the highest up in the tableau. The pivot row and the pivot column are rows and columns labeled by the leaving variable and entering variable respectively. The pivot entry is the entry in the tableau, in the pivot row and the pivot column. Determine the new basic solution by making the entering variable basic and the leaving variable non-basic. Go to step 1. In a maximization problem, having all such constraints, the starting solution will have a set of basic variables consisting of the slack variables in the problem. So we have an example. Maximize z is equals to 5x1 plus 6x2, subject to 3x1 plus 2x2 is less than or equal to 120, 4x1 plus 6x2 is less than or equal to 260, x1, x2 is greater than or equal to 0. In standard form, we have maximize z is equals to 5x1 plus 6x2 plus 0s1 plus 0s2, 4x1 plus 6x2 plus s2 is equals to 260, x1, x2, s1, s2 is greater than or equal to 0. The simplex operation are performed in a tabular format. By setting x1 and x2 equal to 0, we have initial solutions. S1 is equal to 120, S2 is equals to 260, and Z is equals to 0. The basic variables are noted in the first column of the tableau, and their values are read from the last column. Here we see we have basic variables where we have Z, S1, S2, then we have Z, X1, X2, S1, and S2, and the solution. In the current Z row, both variables x1 and x2 have negative coefficients. Since we are maximizing z, the value of z can be improved by increasing either x1 or x2 above the 0 level. In the above tableau, the most negative coefficient in the z row is negative 6. So the minimum is 120 divided by 2, 260 divided by 6. We get that the minimum is 260 divided by 6. So the new tableau is given by x2 entering and s2 leaving. Note that x1 has replaced s1 and x2 has replaced s2 with s1, and s2 becoming non-basic variables. Values of z, x1, x2 are read from the solution column as z is equals to 280, x1 20, x2 30, s1 is equals to s2, which is equals to 0. Since all the 0 z coefficients are non-negative, this solution is optimal. Let's take another example. Maximize z is equals to 20x1 plus 30x2. x1 plus x2 is less than or equal to 10. 3x1 plus 2x2 minus 18. x1, x2 greater than or equal to 0. As we maximize, we can see that the simplex operations are performed in a tabular format. In the above tableau, the most negative coefficient in the z row is minus 30. So the minimum is 10 divided by 2, which is 5. So the new tableau is given by The minimum here we get is 4. 8 divided by 2. So S2 leaves and X1 enters. So the basic feasible solution, x1 is equals to 4, x2 is equals to 3, max z is equals to 170, s1 is equals to s2 is equals to 0. So the values of z, x1, x2 are read from the solution column as z is equals to 170, x2 3, x1 4, s1 is equals to s2 is equals to 0. Since all row 0 z coefficients are non-negative, this solution is optimal. Here we see another example. X1 enters, the minimum a half, 5, 1 is equals to a half, and S1 leaves. So that is all. In the coming videos, we are going to be looking at different evaluations of these programs. Thank you.